Welcome everybody, Coffee with Caleffi, here we go again. Hey, we've got a really fun and interesting presentation put together today. Cody did this was his idea, his topic, and he's done a great job with it. Some new content, I think you'll be really excited and interested in this. So we've got a couple housekeeping slides here. I'll introduce Cody as my brother in brass, I guess. He's the other trainer, other educational manager at Caleffi, so we both share the same job, and these days a lot of that's been virtual, but we chatted a little bit before the start and caught up. So let me do a couple housekeeping slides here. So there, yeah, if you do have problems with the logging in with the audio or something like that, that's a tech support number at GoToMeeting. That's not our tech support, by the way. So if you have a problem or something, you can call them. Sometimes they can talk you through a connection issue or something like that. And yes, at the end, there'll be a little bit of a survey. And if you click that you want the presentation, we'll send you a PDF of that. So that'll be right away at the end of it. And then give us a couple days. It will be archived on our YouTube channel. So if you want to watch it again or share it with somebody else in your office, we'd love to have you do that. So just, search for that and you'll find it. Yeah, these should be in your mailbox. It should be on your desk, hopefully. This is issue number 27 of Hydronics. There's a hot topic right now. We've covered this a couple times. Siggy's done a couple presentations on this for us, and this is something to watch. If you're not involved with this technology, keep an eye on this. But yeah, that was issue number 27. And I think we had another thing on hydronics. Yeah, so what we're doing with the hydronics now and going forward, and then we're going to get to the back issues, is we're putting a digital version online also. So now you've got the ability to get the hard copy if you like to have those in hand. I do. I like to make notes in it. It'll still be on the website as a PDF file if you want to download it and use it that way. But also we're doing this, I think probably most of you know what that is, where you just kind of scroll through the digital version of it. So I think we've got a couple of them up and going already, and the new ones will be all digital also, and then we're going to go back and do the previous ones will be converted into a digital file also. So there's our boy. I know he's got a lot to cover, so I'm going to let him get right into it. I'll be fielding questions. I see a couple of them came in already, and then I'll interrupt every now and then if there's a good question, and if there's time at the end, we'll do some more. But either way, we're going to get to all the questions either online or we'll answer them offline. So take it away, Cody.
Perfect. Well, thank you very much, Bob, and thanks everybody for attending today. Like Bob said, we're going to be talking about 10 things to avoid when you're designing a hydronic system. In a lot of our webinars, we tell you what best practices are. We tell you about things that you should do to make it work correctly, but we kind of put a little bit of a different spin on this today. We wanted to talk about not only what happens when you do it right, but what is going to happen when you do it wrong. So that way you can catch these things when you're working on those systems as well. So we've got a lot of great topics that we're going to cover in today's webinar. And like Bob said, if you guys have any questions, don't hesitate to jump in there in the questions pane and answer them. If we don't, and ask them. If we don't get them today, we'll definitely get back to you as soon as we can. So let's jump right into it. When we talk about pressure, let's just start at the beginning with your design. And you might have a system designed or even installed. You need to fill it up with water or fluid. That water or fluid is the conveyor belt that takes the heat from one point to another in your system, and the pressure of that system is often overlooked. So you want to avoid pressures that are too low. You also want to avoid pressures that are too high, but what is too low or too high, and what's just right? What's that Goldilocks kind of scenario for you? So first, let's look at static pressure. Got a nice little image there on the right-hand side of your slide. Static pressure is the force exerted by water at a given depth. Okay, so what we've got on that little image there on the right-hand side is a 10-foot column of water. And you'll notice at the very bottom of that 10-foot column of water, you're going to have 4.33 PSI. But if you were to actually take a pressure reading at the very tippy top of that 10-foot column of water, you're going to read 0 PSI and probably right around 2 PSI somewhere in the middle. So from this logic, if you've got a system where you've got a fill point, a hydronic system with a fill point at the bottom, you're technically going to need 4.33 PSI to push water up 10 feet, or roughly 0.433 PSI per foot. And if you want to round up just to make things easier, about a half a PSI per foot. Okay, but let's say that you fill this column until your gauge at the bottom reads 3 PSI. That 3 PSI would only get you roughly 7 feet up. And if this was your hydronic system and it was 10 feet high like this column, you now have a big pocket of air at the top, and you're going to have a big problem because, as we all know, these systems are supposed to be filled with water, and you're going to have a no heat scenario. So in most cases, the fill point of your hydronic system is going to be at the bottom. So let's just take a quick example here of a 2-story building with a basement, 8-foot ceilings, and you need to get from the basement to the baseboard, the fin tube baseboard at the 2nd floor. Let's just say this vertical height is 16 feet. So in this 16 feet, what we learned from this column of water, if you take 16 feet and multiply it times 0.433, you're going to need roughly about 7 psi, okay? So if you need 7 psi to get to the top to get it all filled with water, why are we designing a 2-story, average job like this with 12 psi? Why is 12 psi that magic number, especially for those smaller residential jobs and light commercial jobs? The reason why we have that 12 psi is because that extra 5 psi allows us to have positive pressure at the very top of that system. Okay, the positive pressure is what's going to be required to force any air out of any typical type float type air vents, or even if you've got a coin vent at a baseboard or a copper fin tube baseboard elbow, you need that positive pressure at the top to force that air out. Okay, so that 5 psi is going to give you that little safety factor that you need. Okay, now the one thing I'm going to tell you about air vents, just by their very namesake, they're really good at letting air out, but they're also really good at letting air in. Okay, so if you don't have a positive pressure at the very top of that system, any air vents under certain scenarios where you could potentially have less than 0 psi or a negative pressure could actually be letting air in, which not ideal when we're trying to get all the air out of these hydronic systems, and it's just going to cause you more grief. Now, we do have an interesting little accessory. We call it the anti-suction cap. Now, there's 2 parts to this little anti-suction cap, and in the base of it, there's actually a small check valve. This allows air out, but it does not allow air in. And what I noted here is that this product, I believe it is just what I note here, is that it's a Band-Aid. Okay, it's a Band-Aid to cover up a larger problem like incorrect fill pressure or possibly an incorrect location. Okay, the next thing you need to make sure, if your pressure is too low, that you need to make sure of, you need to make sure you are meeting the net positive suction head requirements for any larger circulators in your system. Okay, so if your pressure is too low, you're not meeting these requirements for the net positive suction head, it can lead to cavitation in these larger circulators, which will certainly lead to an early death of the impeller. Okay, it can also lead to cavitation in control valves as well. So if it does happen to sound like your circulator has gravel chugging through it, just take a little step back and evaluate that system. Okay, now if that larger circulators at the bottom of the system way down here, you're going to have that positive suction, so it's not going to be that big of a deal. But if it is up at the top, you need to make sure you maintain those requirements. So let's take a quick look at the opposite end of the spectrum. Okay, I got a call a number of years ago from a guy who was working on a multi-story apartment building. It was actually 6 stories tall, and roughly the vertical height of that hydronic system was roughly 58 feet. Now, this is where it gets a little interesting. Okay, you take that 58 feet and you times it by 0.433, and basically, at that point, if you're filling from the bottom of the system, that you need 25.114 psi to get to the top of that system. Now, the issue with this particular system is that the boilers were at the bottom, and they decided to install residential boilers that had 30 psi pressure relief valves in them. So now you've got a system that you absolutely have to have 25 psi to get to the top, but you also need to have that positive pressure to go along with it. So their biggest issue was they tried to get it to roughly 27 psi to give them a little wiggle room before that PRV blows. But then all of a sudden they have issues with an expansion tank, and they have issues with all these other things where that pressure is going to creep up and those PRVs are going to blow off. So hindsight being 2020, which it always is, maybe it would have been more ideal to have the boilers up at the top of that system so you can maintain 10, 15 psi up here. And maybe down here it's going to be 35 or 40 psi, but it really doesn't matter because those PRVs are going to be up here instead. So, again, you want to avoid pressures that are too high and too low. Whenever you're designing those systems, take that height of the system, times it by that 0.5 psi and add a little bit, and you're going to be in that safe zone. Now, the next thing we want to talk about is the point of no pressure change. Okay, the point where your expansion tank connects to your system that is the point of no pressure change. Any increase in pressure at this point will be basically soaked up by the air cushion in that tank. And what you want to do is avoid pumping into that expansion tank. It is best practice to always pump away from where the expansion tank connects to a system. As a matter of fact, our good friend in the industry, Dan Holohan, has a whole book, Pumping Away, about this very topic. So when you look at this diagram, just note that this loop here, and it's all at one level, there's no height difference to it or anything like that, but this entire loop has been pressurized to 5 psi. The circulator is going to induce flow by creating a pressure differential, but with that circulator pushing into the expansion tank, it has to look elsewhere to create its differential, so it pulls from the suction side. And that circulator, like I said, it uses that differential to move the water, but you'll notice as the fluid moves around that system, it starts to lose pressure due to friction losses in your elbows and your piping. And sooner or later, it's going to come to that third elbow where now all of a sudden it's at 0 psi. Gets to that last elbow, it's negative 2 psi. Now we talked in the last slides here where, you know, if you've got an air vent anywhere in this system, you're going to have the potential for letting air in, which obviously you want to avoid, not only for noise, no heats, oxidization, and all these other issues. So, you know, you want to try to avoid this as much as possible. You want to pump away from the expansion tank. So from there, here's what happens when you do pump away from the expansion tank. Okay, it's gonna create that positive pressure, that differential pressure on the outlet side of the circulator as opposed to the suction side of the circulator. It's gonna maintain positive pressure throughout the system, which is gonna help discharge air from vents, which is great. It's gonna help also to keep air in solution. So that higher pressure is gonna make sure those air bubbles are a little bit smaller, make them easier to push around the loop and come back to a central air separator. And it's also going to minimize pump cavitation as well, which is obviously ideal with your larger circulators. But one thing I do want to impress on you is that you always want to double check the tank charge for your expansion tank. You know, just because it says that it's at 12 psi doesn't mean that it actually is. And if your fill pressure isn't 12 psi, you need to make sure that your expansion tank pressure and your fill pressure matches. So that way you're not losing any acceptance value or losing any capabilities of that expansion tank. So definitely do that. Now, one of the questions that we actually got in from registration, and I'm going to tap you on this one, Bob, just to see what your thoughts are. We got a question from Mark. He asked that, is it ever acceptable to use multiple expansion tanks instead of one large expansion tank? And what are your thoughts on that one, Bob?
Yeah, definitely. I mean, that's sometimes a good way to do it to save low cost, as long as they're in the same location. You don't want to put one there by the circulator and then put one somewhere else out in the job. And I talked to Dan Holohan about this recently. He said, you know, that would happen back in the days is cast iron radiators would act as a second expansion tank. There'd be a big air bubble in the top of a radiator somewhere, and it was kind of fooling the system, thinking that was another point of no pressure change. So yeah, as long as they're in the same location and pre-charged to the same, you know, pressure before you connect them into the system, I would say.
Perfect. Yeah, and I'm in the same boat. You know, I mean, if you've got 2 expansion tanks that will meet the requirements of the job laying around the shop, you know, go ahead and use them. Sometimes you don't even have room for one of those larger expansion tanks, but you got room to fit 2 smaller ones in another spot too. So as long as they're sized appropriately, you know, knock yourself out on that. So Glycol, you guys have probably all dealt with it at one point or another. It's pretty common in applications like vacation homes or areas with extreme cold like Canada. But if you're planning on Glycol for an existing system, you're going to be retrofitting or adding Glycol to an existing system, I would strongly encourage you to avoid any potable feed to that system, especially when accompanied by an autofill type device. If you happen to have a leak in this particular system, you know, the customer went to all the trouble of having you out, paying for that Glycol, getting it into the system, you know, in hopes that it'll keep their system from freezing and causing issues in the event of a no heat. If you have a leak, an autofill is going to bring that pressure back up. It's going to do its job, but in the process, it's going to dilute your Glycol. And the building owner or the homeowner is going to be none the wiser. Okay. Now, in most cases, leaks are pretty easy to spot. Okay, they're going to have a wet spot under a baseboard somewhere or whatever the case may be, but other times, not so much. Now, in my neck of the woods in southern Wisconsin, one of the things that they did throughout the 50s, 60s, and 70s was put soft copper in concrete as a form of radiant. Again, pretty popular in my area, and it's not so popular anymore, obviously, but a leak in a system like this could potentially go unnoticed for years, okay? You know, I actually had a customer, really entertaining customer. He called up and he wanted a quote to install an autofill on an existing system that was a house from the 50s or 60s, and I said, well, gee, Mr. Customer, I am certainly intrigued. You know, why do you want to install an autofill? You know, as technicians and engineers here, we know that these systems should be watertight and not lose pressure or lose any fluid. And so he said, well, I have to go down there and I have to manually feed more water in there to bring the pressure back up, probably once every couple of weeks. And so, you know, again, being the intrigued fellow that I am, I asked, well, where's that water going? You know, why are you losing water? Why do you have to add more and build up the pressure? And he said, well, I don't know. And so from there, I talked him into doing a regular maintenance on the boiler. I said, let's go out there and check over the boiler, see if there's anything, you know, easy to spot. Well, it turns out he had that soft copper in concrete for a radiant system there. And it was at that point that hindsight, again being 2020, I wish I would have had an infrared camera. Okay, I told him, I said, I'd bet you quite a bit of money that you've got a leak in that copper infloor, and you know you're not going to see it because it's going to drain out underneath. He would not believe me, and again, I wish I would have had that infrared camera. I could have showed him the big red spot in his floor. Never heard from him again. So hopefully he got that taken care of. He probably thought I was nuts wanting to dig up his concrete or anything like that. But I wish I would have had that infrared camera for sure.
I would say use it sparingly, Glycol, because you know it brings some baggage with it as far as heat transfer,
sure.
Leak potential and stuff like that. But there's some times when there's piping in an exterior location or obviously a snow melt where you have to use it. So use it wisely, I would say, Cody.
For sure. Yeah, I mean, you're going to have some penalties on your pumping power, heat transfer as well. So like Bob said, use it sparingly. So if you got a residential job, maybe you can get away with 30%. But yeah, you start getting into those snow melt systems, you know, you're probably going to go 50-50 in most cases. So if I'm telling you to avoid an autofill, you know, an autofill is there to make up any fluid that's lost or make up any volume due to blowing down Y strainers or dirt separators or any volume lost to air separation and things like that. So you still need to have makeup water in these systems, and a lot of times what we see nowadays is these glycol feeders. Okay, there's a number of different manufacturers. You fill up a bucket, it's got a little pump on it. They work really great, but we were just looking at something a little bit more homemade. Okay, and Bob, if you want to jump in on this one and talk about your pig here.
Yeah, it's just basically take an expansion tank and pump it with some glycol and put a pressure reducing valve on it there and just tie it into the system. You'll find those typical number 30 expansion tanks. You can jam about 3.5 gallons of glycol in them. So there's a little bit of capacity that if you do have some air purges out, you've got some fluid to go in behind it. You won't get a lockout condition on a low water cutoff switch or low pressure switch. But you're going to know if all that 3 gallons of glycol disappears the first week you put that in there, it's time to start looking for a leak. You've got more than just air evacuating out of the system. But it's a fairly simple, inexpensive way, and it's portable. And where I first started using it is when I was filling up solar thermal systems. Instead of dragging the pump and the hoses and all the stuff down into somebody's basement, you could just pre-charge a tank like this and squirt it into the system. So it can be used as a way to carry the glycol and inject it into a system or boost up a system that if you don't want to take your pump and buckets in, you can carry it in like this, or like Cody said, as a maintainer. In this case, I would call it a glycol maintainer.
Yeah, and so this is actually your system, or one of your systems, Bob, I believe, over here. And this is one that I was actually messing with in our lab here in Milwaukee. Like Bob said, you get an extra 30, you can jam a couple gallons or, almost a little over 3 gallons in there, and it's going to do a great job for you. Okay, now, most of your common boilers these days, your high efficiencies especially, are going to have some type of pressure sensor in there to lock out on low pressure. Obviously, your cast irons in most cases are not, but either way, a low water cutoff is going to be a great backup or insurance policy to make sure that if you do run out of fluid, it's going to shut everything down before things get really ugly. So, you know, and going back to those soft copper systems with an auto feed on them, you know, I've had jobs too where I've suspected leaks and things like that. But another common thing to check for leaks in those systems, beyond just turning off the incoming water feed and watching the pressure drop over time, I've seen guys install water meters on the fill going to the boiler. You know, you can check that clock on the water meter. If it goes up the next time you're out there, then you know you've got a leak somewhere, you're adding too much water. And if it's, you know, tens or hundreds of gallons, then you know you got a big leak somewhere. So definitely something to look out for. Now, we do have a quick poll question for you guys. You might have noticed a number of simple piping schematics that I've produced for this webinar. Now, if you're not already aware, we make drawings available for all of our products, and we do have a pretty heavy engineer base for these Coffee with Caleffi webinars. So I want you guys to remember that we do already have these drawings available on our website. We have them in 2D, 3D, BIM models, as well as things like Visio stencils as well. So we have a quick poll question, and Mary, if you want to jump in on this one, we want to know what you guys are doing here. So it looks like Mary's got the poll open there. Thanks, Mary. How do you guys produce system drawings? We want to know if you're using an AutoCAD or similar type program, any of your BIM programs, like what you're working with there. Maybe you're not quite to that level. You're using SketchUp, Visio, or a similar type program. Maybe you're fortunate enough to use a bar napkin or a big chunk of the cardboard off of the box the boiler came in, whatever works. Or maybe you just don't have a need for drawings at all. So definitely type into that poll or click on that poll. We were curious to see what you guys are using. And again, with a heavy engineer base, I think a lot of our answers here are going to be in the top two, but we'll see what happens.
Yeah, you're right, Cody. It's AutoCAD or similar is 36%, Revit or BIM programs 22%, SketchUp 16%, I hand draw 23%, and no need for drawings is only 3%. So that's good. Most people are documenting of some using some method to document the system. So that's good to see.
Cool. Well, thanks again, guys, for that one. We appreciate your input on this. So let's jump right back into it again here with hydraulic separators. Okay. Hydraulic separators are a great device. They allow you to separate or basically differentiate your boiler loops or your chiller loops from your load loops, your system loops. The idea with a hydraulic separator is that you can have a flow rate going to your boiler and you can have a flow rate going out to your system, and they're not going to conflict with one another. The idea with hydraulic separation is to prevent pump conflict in any two circulators that share common piping, like this hydraulic separator here. So hydraulic separators can make our jobs a lot easier, and devices like our Step 4 here, you can see on the right-hand side, they've got a coalescing element and a stack of rare earth magnets and a drywall at the bottom, so they even offer features like air separation, dirt separation, and magnetic separation. But I want to talk about how installers and designers can take these awesome devices and make their lives more difficult, okay? So what I want you to remember, one of the biggest rules with hydraulic separators like this one is that you always have hot on top, cold on bottom, okay? So that warmer fluid going through the top connections, the cold, cooler fluid going through the bottom connections. Now, if you can remember that, the next thing I want you to remember is source on one side, load on the other, okay? So hot on top, cold on bottom, source on one side, load on the other. They are not directional, so you could have the source on the right and the load on the left, but you need to make sure the supply and return for the source are on the same side and the supply and return for the load are on the same side. Okay, so let's talk about what happens when you don't follow these rules. Okay, so in this particular case, we've got the returns coming back on the top, the supplies going out on the bottom. And in this scenario, I want to stress the fact that hydraulic separation is still going to be maintained. Okay, you've got this big barrel, this big low velocity zone of the barrel. You're not going to have any pressure drop through here. So this circulator could be 100 gallons per minute, and this one could be 10. As long as this device is sized properly, it's going to work great. Okay, but where you're going to suffer, or the problems you're going to have, is that you've got a common return coming back on the top here, hitting that coalescing element, and any dirt and debris that comes into this separator is going to want to fall down through the barrel, But instead of falling down from this lower connection here, it has to fall down through the barrel all the way through and then go through the flow path for the supplies going out to the system, and then hopefully make it down to the bottom of the barrel. Now, there's no guarantee there that this flow rate or this flow going through the barrel, through the lower connections, isn't going to take that dirt and debris back out into the system again, okay? And the same thing holds true on the bottom here. You've got your high temperature water, and hopefully we all know by now that your air separation is going to be best when the fluid's the hottest and at the lowest pressure. So you'll notice that we're pumping away from the hydraulic separator with both of our circulators. But you've got that coalescing element that's going to collect all those little air bubbles, and instead of having direct access right to the air vent at the top, now those bubbles have to travel all the way up through here, and again through the flow path of the return, potentially back into the system again. And you just don't want to do that. You want to make your lives easier. You want to make sure that you're getting good air and dirt separation, and it's doing its job. So the reason why, well, first, again, don't do this. So again, hot on top, cold on bottom. But the reason why most people are putting the colder water on top and the hotter water on bottom is because they're trying to avoid crossing over their piping. Okay, now obviously in most cases this is a field decision. Okay, they get in the field, they have their boilers hung on the wall, they've got their hydro separator there, their hydraulic separator. The idea of crossing over piping means you're going to have to add fittings, you're going to have to add space, it's going to cost money and time and all this screwing around. So they say, well, why can't we just put the cold on top and the hot on bottom? Okay. Now, this is not just limited to a poor field decision, okay? This is something that I even saw so recently as last week on a drawing from an engineer, okay? Where they put the cold on top and the hot on bottom, and I had to explain and correct everything, and now we're all on the same page. So if you're not putting hot on top and cold on bottom, you're just gonna run into some issues there.
Hey, Cody, can I interrupt too?
Yeah,
Expansion tank. Somebody asked the best tie-in for the expansion tank on those separator pictures.
Oh, perfect. That's a great question. Okay, so a lot of our hydraulic separators have some fittings here and there on the hydraulic separators, and I'll get to that in a second. But the best place to put your expansion tank is going to be either on the return here, just before the circulator going into the boiler, or somewhere on the return header, on the system side. Okay, it can be right up tight to the hydraulic separator. It could be off the end of the header. Really not that big of a deal. But again, because you always want to pump away from that hydraulic separator, you want that expansion tank to have basically direct access to this hydraulic separator. So if it's right here or somewhere in the return header on the system side, that's going to be where you're going to put it. Now, the place where you really don't want to put it is, again, where, especially field decisions, people see the path of least resistance, and they see this fitting right here at the bottom, okay? And they'll take that off and they'll tee into it, they'll add their expansion tank and their water feed, and that's something that you really don't want to do, because as you have debris settle out of the flow path with that dirt separation device, that dirt is now going to drop through that fitting and through your piping, potentially onto the top of your expansion tank diaphragm. And then if you do have any need for makeup water, because you should have your expansion tank and your makeup feed right in the same spot or the same connection, now all of a sudden you bring makeup water in there, it's going to stir up all that dirt and debris in the bottom, and it's going to potentially bring it back out in the system. So don't take the path of least resistance, add a fitting over here somewhere, and bring that expansion tank in and that water feed. So good question, Bob, thanks. Now here is the very definition of crisscross applesauce. I want to thank my 6-year-old daughter for helping me name this particular topic. Okay, now on one side here we've got a circulator, or the cooler water on bottom and the hotter water, the supply water, going in the top. But on the opposite side we've got them again crisscrossed. We've got the returns coming back at the top, and the supplies going out at the bottom. Now, again, I want to stress that in this scenario that hydraulic separation is still going to be maintained, okay? But not only are you going to have issues with air and dirt separation like we talked about on the last slide, now all of a sudden you're going to have issues because you've got hot water coming in here and you're expecting it to go down through the barrel and out this bottom port. And then you've got return water coming back from the system. You're expecting it to go down through the barrel and through this bottom port here. And the biggest problem with that is you're going to take hot water and return water and you're going to mix them all together. So that means you're going to mix up your return water temperatures going back to your boiler. You're going to mix down your supply water temperatures going out to your system. And obviously that's less than ideal. You're not getting the water, the temperature water that you need out to your system. You're going to raise your return temperatures, which is not good for your modulating boilers. So don't do that either. Definitely avoid that at all costs. All right, now let's jump to water quality. You'll note that I've got not one, but two, but three asterisks at the end of this one. So I'll get to that in a minute. But in many systems, chances are good that you're filling with site water. Okay, I'm curious, and you guys can type into the questions pane. Bob's keeping an eye on that. How many of you actually test your site water before you fill that boiler or that hydronic system? Okay, now maybe you do, but what about your competitor? Okay, well, you know that contractor down the road that's got the stellar reputation. Okay, chances are he's not testing it. Okay. What I really want to impress upon you guys is just because you can drink the site water does not mean you should fill your boiler with it, okay? Many manufacturers out there, especially for the high efficiency boilers, are getting very, very detailed with their water quality specifications in their manuals. And based on the map above, a vast majority of water supplies are not going to meet these strict requirements, okay? So what you want to avoid is the scenario like we see here on the right-hand side is you got a boiler heat exchanger that's all scaled up, it's going to fail, and then all of a sudden you're going to have to be going back to your customer and say, hey, look, you know, warranty was rejected. I'm not going to be able to get this part for free for you, and you know, hopefully let them down gently, and you know, you don't have any big problems. But you want to avoid that at all costs, okay? Now for the asterisks, if you are testing your site water and it does meet the requirements, fantastic. Go ahead, use it all day long. Count your lucky stars is all I can say. Coming from this big area in the Midwest and up through Canada that's bright red, that's got really hard water. Again, we would really appreciate some of that good water over here. Now let's talk about the different types of water that you could potentially be filling your system with, okay? First is gonna be untreated water, okay? Meaning water straight from your tap, your municipal water supply, or your well, or whatever the case may be. If you live in an area like mine, you know, where we've got really hard water, you're gonna have an extreme risk of scaling. Okay, we've got a high content of magnesium and calcium. I'm sitting at my house at roughly 28 grains of hardness. But because you have all those dissolved solids in that system, you're also going to have a high risk for galvanic corrosion. Now, galvanic corrosion is something you typically see in potable systems, domestic hot water systems, which is why it's so common to see dielectric unions and dielectric nipples in those systems to prevent galvanic corrosion between dissimilar metals. But it can also happen in closed loop systems as well. Now, what usually makes it less common in hydronic systems is that in order for galvanic corrosion to happen, you need to have conductivity in your water. That's the dissolved solids. You also need to have dissimilar metals. On the nobility scale, for example. So we have those all the time in hydronic systems, but the other thing you need is oxygen, okay? And if you have good air separation, good air separation and a good tight system, the oxygen is going to be at a minimum, so it's not going to be nearly as bad as what you find in potable systems, okay? So definitely want to avoid those two things. Now, let's just say instead of untreated water, you fill the system with softened water. Okay, now when you do a water softening process, it's an ion exchange that is going to exchange magnesium and calcium for sodium. Okay, so that's going to significantly reduce the risk of lime scale or scaling in your devices, like that heat exchanger we saw in the last photo. But it's not going to do really anything for your issues with galvanic corrosion. Then from there, we take that softened water, we add chemicals. If you go down that road, I'm going to tell you right now, that's a road that you're never going to see the end of, okay? As soon as you start adding chemicals to a system, you're trying to do the best thing you can for that system. I totally get it, but now you're going to have to check on those chemicals. You got to maintain those chemicals. You might have to flush the system sooner or later to basically get it back up to snuff, okay? So the idea there, though, is those chemicals are going to keep all that stuff in solution. It's going to, reduce some of those risks. But again, it's something that you're going to have to deal with for the rest of that system's life. So in a lot of cases, what we're recommending is demineralized water. Okay, demineralized water is a very similar process to water softening, but instead of exchanging magnesium and calcium for sodium, we're exchanging all of the dissolved solids for basically what amounts to more water. Okay, so you're removing all the magnesium and calcium, you're reducing all of that conductivity in the water because your dissolved solids are gone, so you're not going to have any issues with scaling, you're not going to have any issues with corrosion, and you're going to be good to go. Now, engineers, okay, I really want to pound this in here, okay? Water quality standards are something that you can specify, okay, on your drawings, okay? At the very least, you can note that the water quality standards set by the boiler manufacturers need to be adhered to, okay? At the very least, you could do that, okay? So don't be afraid to do this, okay? You're designing a system hopefully that's going to be energy efficient, but you also want it to last, okay? And water quality, you know, basically it's been going around, you know, and it's pretty constant that water quality is the next frontier in efficiency in these systems, because if you've got a lot of debris or dissolved solids, you're going to have a lot more issues with heat transfer, obviously. So definitely keep that in mind. Now, we just wanted to push one of our next webinars. Now, obviously, next month we're going to be talking about booster systems in potable water systems. But the month after that, Bob and I are actually going to be talking about cleaning, purging, and filling hydronic systems, and some tips and tricks that might help you get those systems up and running. So definitely tune in for that as well. Now, velocity. When we talk about velocity, it comes down to the flow requirements of the system and the sizing of the pipe that you're using, okay? So you want to avoid velocity that is too low. You also want to avoid velocity that's too high. So we kind of have that Goldilocks scenario again here as well. So this begs the question, you know, what is the right velocity? Okay, now the right velocity is really going to depend on the materials you're using. Some of them are more resistant to higher velocities, but you know, say for example, you get copper. Copper in most cases, you usually want to maintain somewhere between 2 and 4 feet per second, sometimes a little bit higher on some of the larger piping. But the reason why you want to make sure you're at least maintaining that 2 feet per second or a little bit more is because you need to be able to move air around a system, okay? If your velocity is too low, it doesn't have the ability to push that entrained air or those little air bubbles around to bring it back to your central air separator, okay? Velocity that is too low due to oversized piping or an undersized circulator is usually pretty rare, but it does happen on some of these gravity converted systems and steam systems conversions as well. You can also have issues with heat output and heat transfer. Just because of the fact that you don't have the velocity, you don't have that speed, you don't have the turbulence that goes along with it through either a plate heat exchanger or a terminal unit, a fan coil, whatever. So you could actually run into less heat output as well. Same thing goes with dirt separation and dirt removal in your system. You need velocity to push that dirt and debris around the system in order to bring it back to a Y strainer or a dirt separator like what we have there on the right. So, you know, I always mention to guys that's, you know, it's a necessity to have these air and dirt separators in the systems to protect your boilers, protect your circulators, and protect your system in general. But the thing to remember with air and dirt separators is that they can only catch what comes to them. Okay, so if it's floating out there in this huge distribution system, if it never comes back to the dirt separator, how are you going to get it out of there? Okay, so you need to maintain these slightly, you know, basically this Goldilocks scenario velocities in order to get that stuff back. So 2 to 4 feet per second at a minimum kind of thing. You know, if you are cleaning and purging a system out on a new installation, you're going to need higher velocities than that. So keep that in mind, because if you're sizing your pumps and your piping appropriately, chances are those circulators are not going to be enough to move around some of the larger dirt and debris. So you need to bring in a flush cart in a lot of cases to get that flow up there. Now, when it comes to velocity that is too high, okay, the first thing you're going to note is that it's going to be noisy. So if you've got baseboard in a bedroom or something like that, you know, you're going to have complaints of noise. Sooner or later, you're also going to have damage to your piping, okay? Typically, where you're going to see damage to piping due to velocity is right after an elbow, okay? You've got that high velocity going into an elbow. It comes out all turbulent because it gets bounced all around, and then you're going to start pinholing, okay? So that's going to be your first one's going to be noise. The second one's going to be damage to piping. But then, you know, by having that higher velocity, by maybe that piping's too small or whatever the case may be, you're going to run into excess head loss. You're also going to run into the need for a larger circulator, which in turn is going to lead to a larger expense for the circulator and more power consumption for the life of that circulator as well. So definitely keep that in mind when you're talking about velocities that are too high. It's usually a big trade-off. You bring down the size of that pipe, it costs you less in piping, but now all of a sudden you got to have a bigger circulator too. So something to avoid there. Now, we talked about hydraulic separators before. We didn't really touch on sizing. Now, if you don't size these guys properly, your velocity could be too high through this barrel here. And if you've just got one side of the hydraulic separator running, you could have the ability to have too much pressure drop, or the potential for too much pressure drop through this barrel, which could actually force flow out into the system side without a circulator ever being on, okay? So when you talk about velocities that are too high, usually we're gunning for right around 1/2 foot per second in the barrel of these hydraulic separators. If you start going over that, your head loss is going to be a little bit more in that barrel. And again, you have the potential for ghost flow, which you obviously want to avoid. Now we've got some more asterisks here, so kind of bear with me here, but another thing that you want to avoid is low return water temperatures, okay? Especially in a boiler that's not designed to be a condensing boiler, okay? We've got a nice little picture over here on the left-hand side of a boiler that was never meant to condense, okay? Being an aspiring fat guy, my own personal mantra is that any pizza is a personal pizza if you try hard enough. And I believe it was John Siegenthaler that took my mantra and spun it around for hydronics. And he said that any boiler is a condensing boiler if you try hard enough, okay? Or don't try hard enough, for example, in most cases, okay? So on a cold start cast iron boiler, you're always going to have a little bit of condensation on startup, but what you're trying to reduce is sustained condensation in the boiler, okay? That condensate is highly acidic, and what you're going to find typically, the first victim of condensation in a boiler that's not supposed to condense is usually single wall flue piping. So if you've got 26 gauge single wall going from your boiler to your chimney or your flue or your B vent or whatever, usually that's the first thing that's going to start causing you issues. It's going to pinhole. It's going to look terrible, kind of like the hood here on this cast iron monster. Okay, so another thing that could cause it is short cycling of the boiler. It doesn't come up to temperature the way it's supposed to. You'll note here in the little diagram here that in most cases that the magic number for too low of return water temperatures is 130. Once you start getting below 130, you have the ability to condense those combustion gases, and that's what high efficiency boilers are meant to do, to take advantage of that change of state to get a little bit more heat out of it. But it could be also that your aquastat is set too low, or maybe your outdoor reset on a cast iron boiler is not set correctly. I actually had a good friend of mine with a cast iron boiler, and he was just dangerous enough as a software engineer to know that the lower the water temperature of the boiler, he has potential to save money. But what he didn't realize was that it was at the cost of his boiler. So we had to correct that as well. So another thing, let me skip back here. Another thing that I want to talk about is how a lot of these cast iron boilers control condensation and sustain condensation is that they a lot of times are doing it with a bypass from the supply and return. The idea here is on a cold start, you're going to actually short circuit some of that hot water right back into the return, and you're going to bring that return water temperature up quickly, again, to prevent condensation. But what happens when you've got long run cycles and your return water temperatures are up, but you're still bypassing some of that supply water? It's kind of wasteful in my opinion and really not necessary, but it's a kind of a cover your rear end mentality out of a lot of these boiler manufacturers with diagrams that are 40 years old. Okay, so instead of using a ball valve or a globe valve to bypass to control those return water temperatures, instead of that, what I would suggest a thermostatically controlled bypass instead. What we've got here is our 280 series. This guy, what it'll do is it'll bypass some of your supply water on a cold start to bring up that return water temperature. But as the return water temperature increases, it's actually going to close off that bypass. Okay, it's basically a really dumbed down thermostatic mixing valve with much higher flow capabilities, and it has a preset temperature of typically like 130 or 140. Okay, so if it's below 130, it's going to be full open to bypass. As it starts to creep above 130, it's going to start closing off that bypass and bring in the supply or the system return back into that boiler. Now here's a really interesting application here that's taking advantage of those low return water temperatures and also keeping the customer's wallet in mind, okay? This is a system where the supply water temperature requirements for this building were quite varying, okay? So much so that, you know, in certain scenarios, shoulder seasons, for example, they might need lower supply water temperatures, which is also going to result in lower return water temperatures, okay? Now, those lower return water temperatures are great for these condensing boilers on the left-hand side, obviously not so great for the non-condensing boilers on the right-hand side. So what they actually have here is a system where during the shoulder seasons, those high efficiencies are doing their job. They're getting that high efficiency, they're getting that change of state and the extra heat out of that that latent heat out of that condensation. But as the demands of the system start to increase and they start staging on more boilers, that return water temperature is going to come up, and then they're going to bring online these non-condensing boilers. Okay, so the idea of kind of this mix and match scenario where you've got condensing and non-condensing is a great way, again, to capitalize on those low return water temperatures and keep your customer's wallet in mind. So this is actually that system brought to life. You can't see it hiding behind here. That's actually one of our hydraulic separators in there, again, coupled with a couple of high efficiencies and a number of non-condensing boilers over here on the right. All righty, now the next thing that I want to talk about is control systems, okay? I really want, you know, being a technician from the field, I really wish we could avoid these overly complicated control systems. And I do believe they have their place in many scenarios, but it's also really easy to design systems that are not overly complicated, okay? Say, for example, here in the diagram, we've got a boiler that's maintaining a buffer tank based on outdoor reset. On the other side of this buffer tank, we actually have a variable speed circulator with a manifold. The home run system, you could also have a, you know, a branch and T type system as well in this scenario, but a home run system is nice for this diagram. And you've got panel radiators with thermostatic control valves on them. This is a really cool system in the fact that you've got a boiler maintaining a buffer based on auto reset. You've got these this variable speed circulator that's modulating up and down based on the thermostatic controls demands. You've got no thermostats, no wiring, no nothing. I mean, it's so ridiculously simple, and it doesn't always have to be complicated, okay? Now, this actual scenario was used in an apartment building. I talked to a customer about a number of years ago where they actually abandoned the pneumatic controls. They put in a big boiler, a big buffer tank over here, and they maintained the buffer based on outdoor reset. And again, large variable speed circulator. And in each apartment in this building, they had a baseboard loop that was all in series. So they had a series loop for each apartment. And so what they did is for each series loop in each apartment, they put a control valve in there, a valve control in here, and they sweat it right in. And then right on top of that, they actually had a thermostatic control that would mount right onto this valve. So now they've got the thermostat built right there. They've got no wiring coming back to the boiler. The boiler maintains the buffer tank. The variable speed maintains the supply going out to that each of those series baseboard loops. And it was just, I thought it was a really interesting low cost option, you know, for these types of scenarios where rewiring a building is going to be next to impossible. Okay, and it's something that you can just make these jobs a little bit easier. Now, we start getting into systems that are a little bit more complicated. There's still ways of making it easy, okay? Now, whether you're talking about how the homeowner interacts with the system or how the controls interact with the equipment, it still doesn't need to be difficult. And in fact, in a system like this is a system where we had 5 zones of gypcrete, thin pour gypcrete, and we had a single zone of radiant in a 4-inch slab in a garage. You can kind of see it's separated by a heat exchanger over here on the right-hand side, okay? I would highly recommend in systems like this, even avoiding just the complexity of basically setback thermostats, okay? In a high mass system like this with potentially an aggressive outdoor reset curve, recovery from any type of a setback is going to be awful, okay? And it might work just fine until you get to that coldest day of the year when it just won't keep up. You know, that call from your homeowner where they have it set to 70 now and it won't get past 68. Well, what they didn't tell you is that they turn it down to 65 every night and it's worked just fine until it, you know, hit about 10 degrees below zero, okay? Now, on the other hand, you know, you might have an older home with envelope upgrades, you know, nicer windows and more insulation, oversized heat emitters like cast iron radiators. Maybe that little guy, that system might be able to handle a little bit of setback a little bit more, you know, without trouble, basically is what it boils down to. But you know, when we talk about controls to the system, the controls and how they interact with the equipment, this particular job left a little bit to be desired for me, okay? Instead of being handed a zone valve control to go to this job and wire up and get it up and running, I was basically left to my own devices. We had little money left in the budget and we didn't have enough for a zone valve control, so I used terminal strips, universal transformers, and rib relays, okay? I MacGyvered this sucker the best I could, okay? And I'm sure we've all seen worse as far as controls are concerned, but I would have traded that diamond plate backing. I would have traded it for a second for a zone valve control. You know, I wouldn't have even blinked twice. I would have traded that diamond plate, no problem, just for a straight up plywood backing, okay? So when we talk about this, we talk about the ability to use basic zone controls. Now we've got a system here that's a little bit more complicated, but not terribly. You've got 3 zones of high temp, you got a zone of low temp, okay, but you've also got an indirect that needs priority, and you've got a boiler circulator as well. So in this particular scenario, the idea of using zone controls is going to help speed up my installation. It's going to prevent those errors in wiring. You'll notice how our zone controls here have they basically switch back and forth between colors on the terminal block so you know which zone is which. And it's also going to help with future service, okay? If you've got a system that has wiring like I showed you in the last photograph, or a whole bunch of those single zone relays floating around, trying to trace wiring around can be a real chore, okay? So it's gonna really expedite future service to make sure that you're in and out of that job a lot quicker, okay? Between this and a great label maker is going to be a godsend for any service technician coming down the pipeline. Now, the other thing that you might not know, and I want to make you guys aware, is that if you are using our zone valves, which a lot of you guys use them, it's one of our bread and butter products, okay? If you combine that zone valve with our zone valve controls, you're actually going to increase the warranty of both devices to 5 years. Normally it's 2 years on the zone valve, 3 year on the control. You're going to increase it to 5 years on both of them, so you get a big advantage there, okay? And next, we want to ask you another quick poll question. You know, we've got your attention. We want to know what you guys are doing, you know, with how you're making drawings. But this is a question more for that base where you're not using AutoCAD or you're not using Revit and things like that. But you're looking for a simple program to allow yourself to make drawings. You've got a system like this where it's or a program like this, it's cloud-based, it's a drag and drop kind of program. Is this something that you would be interested in? Is this something that would make your job, your lives, your business run smoother? Okay, so we want to ask a quick poll question here, and Mary, if you can pop this one up. Thank you, Mary. A program like this, again, cloud-based, drag and drop, really easy. You can export in different formats. Is this something that you would be willing to pay for? We got the answers there: yes, no, maybe so, maybe need a little bit more information, or you just don't have any need for drawing. So if this is a program that'd be of interest to you and it's something that you'd be willing to pay for, we're curious if it's something that we should help you guys with. So Bob, what do you use for making drawings? Is it bar napkins like we talked about earlier?
Well, all the above. I'm a hunt and peck on the keyboard, so I'm not up to speed on some of these CADs, but I like the program that you just showed. That when I do take the time to do a nice drawing, that's the program I like to use. So it just depends on the time and who it's for, I guess. But yeah, so the poll numbers came in pretty good here. So 49% yes.
Wow.
No,
Cool.
34 maybe, need more info.
Cool. Well, that's interesting to know. It's something that we're considering, and you know, again, the idea of making these drawings easier to access and easier to do, you know, again, being a drag and drop type thing is very very good. So thank you very much, guys, for that. So the next thing we want to talk about is mixing valves. we're coming close to the end here, so we're going to try and speed things up a little bit. But what you really want to avoid is pumping into a mixing valve. Okay, we see this all too often. You need a mixing valve to maintain a set temperature to a low temp zone, whether it be in floor or whatever the case may be. And so we see a lot of guys or a lot of contractors out there, and even systems designed that you're pumping into a mixing valve. Okay, the first thing that you need to know is that mixing valves, when you're looking at these guys here, they actually are inversely proportional on the hot and cold inlets. And basically what I mean by that is that as the hot inlet closes off to this mixed valve, the cold inlet opens, and vice versa, and the cold closes, the hot opens, okay? So when you have a call for heat on a zone like this, okay, you're gonna start getting flow on a cold start. Okay, you're gonna start flowing into the hot inlet. Now you're gonna get flow. Now that's no guarantee that it's gonna go where you want it, okay? There's a potential in here where you could actually cross right over the mixing valve and directly right back into the return, as opposed to going out to your heat emitters. Okay, so the next problem is, as the temperature starts to increase, you're gonna start getting that mixed, or that hot inlet is gonna start closing off in the mixing valve. So you're actually going to have potential for no flow out in your zone, and a potential to deadhead your circulator, which is something you really want to avoid. Okay, you want to make sure that circulator has a good long life. So you always want to pump away from a mixing valve. Okay, now we usually don't see it all that much on a system like this, but we've got another scenario here that I'll show you that is usually more common. Okay, so always pump away from a mixing valve. Okay, you always want to pump away from the mixed outlet here. So at this point, by pumping away, you're allowing the mixing valve to determine which side to pull from, whether it be hot inlet or cold inlet, to produce the proper temperature that it was set for. So another neat little product that you guys may or may not have seen on the right-hand side, it's our angle mix. Really cool product for not only low temp space heating, but also for domestic hot water applications, because it is low lead. Really cool because it's got the hot inlet right in line with the mixed outlet. Saves you some of those elbows and screwing around with some of the T and cross type mixing valves. So if you haven't seen that one, check it out. It's a pretty cool product. But this is where we normally see mixing valves get basically misapplied. Okay, you've got a system where you've got a contractor coming in. They've got an older high temp system with a single circulator, and they're going to be adding a tiny low temp zone to that system. Okay, usually a couple loops for a bathroom in floor, or a small addition like a Four Seasons room, or whatever the case may be. Now, in this case, what they do is they add another zone valve, and then they add a mixing valve on top of it. Okay. I do want to address, we talked about low return water temperatures here. Now, if you have a small zone of low temp in floor, for example, 1 or 2 loops or whatever the case may be, you're going to be bringing back low return water temperature, but it's usually not enough to overcome the boiler and produce a sustained condensation in that boiler. But you really got to be careful. There's some, Bob, do you know of any rules right off the top of your head as far as, percentages of low temp to high temp in a system like this? Oh, that's all right. Either way, a small zone, not going to be a big problem, but as you start getting more and more low temp in a zone, you really need to protect that boiler from low return water temperatures, so that way you're not producing condensation in that boiler. But like I mentioned previously, pumping into a mixing valve is not going to do you any favors. Okay, again, always pump in away from a mixing valve. And another good rule in this scenario is, if you're adding a mixing valve, you also add a circulator. Okay, so what you'll notice here is that, again, we're pumping away from the mixing valve, and you'll also notice too that we brought the hot inlet of the mixing valve back here, so we're pumping to these 2 separate areas in parallel, as opposed to in series off the header. Okay, and you're again allowing that mixing valve to do its job. Okay, so again, you need to make sure that mixing valve can do its job and pull from the hot and cold inlet as necessary. You want to make sure that circulator is going to get flow out to that system, or that particular heat emitter. Now, last but not least, I'm sure we've all been down this road before of managing expectations. So after you've avoided millions of other potential pitfalls with the design and implementation of your system, there's this one last thing. There's the unrealistic expectations, which usually should be taken care of before all the trouble of the design and implementation. Okay, But the thing is expectations are really going to vary based on location and even customer to customer. Okay, for example, hydronic heating isn't as common here in the Midwest as it is in the Northeast. So building owners may not be as knowledgeable here, and their expectations might need a little bit of fine tuning. Okay, another thing to avoid is the scenario of over promising and under delivering. Okay, I know Bob's been married a long time. I'm actually entering my 11th year of marriage by mostly abiding by this rule, so definitely keep that in mind. But back to hydronics, quick little story here. Okay, I had a new construction home for a couple. It was being built as their dream retirement home. Okay, and in-floor heating in this house was a huge splurge for them, and they had it in their minds that the floors would just be warm all the time, and that was something that was never dispelled. Okay, so a short while after they moved in, the weather started to turn, the heating started to run, it maintained temperatures, it was running great, except for one thing. That one thing was that the floors were not warm. This customer called, he was kind of upset, and I get it. He wanted warm floors. So long story short, despite my protests and my warnings, I set up those nice thermostats to maintain a minimum floor temperature. Okay. The very next day, I got a call saying that the house was 83 degrees and the heating would not shut off. Okay. So my caution to you on that one is if you want your floors to be warm all the time, you need to make sure that you're not putting too much heat into a house that's got 2x6 walls, spray foam insulation, and triple pane windows. Okay, I told the customer, I said, we talked about this. I said the only way you're going to be able to maintain warm floors and not overheat your space is by opening a window. And I mean, this is the only thing that's going to make sense here. So you're producing comfortable systems, but you need to make sure that you're managing expectations. Does that customer want just the cheapest system out there, or do they want supreme comfort? In short, you guys definitely cover your rear ends on this stuff. Okay, so we're going to go ahead and end it here, but we're going to keep things open. We've still got quite a number of people here. Bob, I don't know if there's any questions that we wanted to answer here at the end. Any good ones that you wanted to bring?
Yeah, I got through, I think most of them. There's a couple of them. I mean, Drew said they sell them AC for the issues of overheating, which is another way to skin a cat, I guess. Let's see, using variable speed pumps and condensing boilers, at what point is a mixing valve needed? Example, 120 supply for the first zone, 100 for the next. Does that?
Oh, as far as when is a mixing valve needed based on how far apart your temperatures are? Is that what you're kind of getting?
That's how I'm assuming he's
Yeah, I
asking.
mean, if you are looking at multiple temperatures in a system, if you're designing this system from the ground up, trying to limit it to 2, maybe 3 temperatures is probably going to be advantageous. If you have a system designed and you've got one zone that needs 130 and then another zone that needs 125 and things like that, well, maybe you could add a little bit more loop on this in-floor zone to bring it down from 130 to 125. But when you start getting into larger spreads like 15 or 20 degrees, then yeah, obviously, bringing in another mixing valve into that scenario would be advantageous for sure.
Yeah, I don't know if there's a rule of thumb out there of 15 degrees. I've heard people say 20 degree spread is when you need to go to another mixing valve. Like you say, it really depends on the type of emitters. If it's a radiant floor and they're going to notice the temperature, certainly I would look at that a little bit closer than if it was a thin tube system or something like that, where they're not, their skin isn't in contact with it, where they can tell the difference of a few degrees. So that was well put. Let me see. I'll do a couple more here. Could you explain on the manifold with the mixing valve and circulator, the H member should be removed or no flow?
Oh, geez. Okay. So I don't know if I had a good slide on that one, but we produce a manifold it's our 172 series manifold. And that manifold, it has a circulator and a mixing valve built right into it. It's a system that we actually sell a lot into the New England area, where they've got a lot of high temp systems, but maybe they're adding an addition of low temp or something like that. So it's great, the fact that it's got a mixing valve, it's got a circulator built right into it, but right below it, we actually have a small hydraulic separator fitting. Okay, the idea here is that if you have a circulator already for your system and you're coming off the end of that header for that off that circulator, you could actually flow to the hydraulic separator fitting on the bottom bottom of this manifold, and then the circulator on the manifold will draw from the hydraulic separator what it needs to provide heat to that particular loop. Now the issue is with those manifolds, I shouldn't say it's an issue, it's only an issue if you don't know, but the issue is that if you are expecting the circulator on that manifold to bring flow from the boiler or the heat source, you need to remove that hydraulic separator fitting in order to allow that circulator to pull from the heat source, okay? If you don't pull that hydraulic separator fitting off, it's just gonna short circuit inside that hydraulic separator and you're not gonna pull any heat from your heat source.
Yeah, I didn't know if maybe one of those schematics you put up there showed our manifold.
You know, I'm not sure. Let me.
Yeah, I know you had some pictures, but I didn't know if it showed the H valve in there. But yeah, I think you explained it well.
Yeah, hopefully. And if you're on our website, you can research the 172 series manifold, and it's right on there. And it's, you know, like I said, that hydraulic separator fitting is a point of confusion sometimes if you don't realize what you're looking at. So.
Yeah, I think question-wise, you got them all. You got a lot of kudos.
Okay.
A lot of people liked the presentation today and thanked you for that. There was one comment, I think from Drew somewhere up earlier about variable speed pumping. He said you got to rev them up every now and then. I think he meant that when you were talking about air removal. If
For
you've
sure.
got a variable speed circulator and it's always revved down, you might not move in the air through the system. So that's a good point that maybe they should have an exercise function built into them that once a day or a week or something, they go up to enough speed to move the air out of the system.
Yeah, and I mean, I'm sure you've dealt with this personally, Bob. So have I. You know, you've got a job where you've got it's pretty well zoned to the hilt, and all of a sudden you got a small zone that circulator's running very low, you know, very low flow rates, and you know you don't have enough flow and enough velocity to start pushing those air bubbles around, and so you know, like I'm sure you did the same, Bob. We tried to purge them out the best we could, you know, on filling to get all those big air bubbles out, but you know, try to get, you know, each individual loop running, maybe blast that circulator up to high speed for a little while, maybe even overnight if you're coming back the next day, and then bring it back to normal again.
And along those lines, the other thing I would suggest is take the boiler up to a high temperature, because the higher the temperature, more you're going to get the air out of solution. So even if your system's going to run at, say, 140-degree design day, maybe run it up to 160 or 180 for an hour while you're there. That'll help get all the air out of solution, and then you know, keep the pump speed up, like Cody said, and keep the temperature up for a short period of time. You should be able to walk away from that system with a good micro bubble air purger on it, and your air problems should be non-existent, I guess.
Perfect. Well, we originally thought, you know, coming into this webinar that a lot of our audience would be a little webinar weary, but I want to thank you guys. We had a great attendance on this webinar, a large amount of registrants and a great attendance here. And if you guys have any questions, don't hesitate to contact us. We are here to help you out and make your jobs easier. And if there are any questions we didn't answer during the webinar or any of the questions from the registration that we didn't answer, I will be getting back to you personally with comments on those. And again, I hope you guys have a great day, and hope business is good. And thanks, Bob, for your help.
Yeah, thanks, everybody.